Hello everyone. In this video, we are going to talk about the variation of g with altitude, depth and rotation of Earth. G is acceleration due to gravity, and on the surface, its value is 9.81 meter per second square. Now let's see how it varies as we go away from the surface, above the Earth's surface. Let's say we have gone a height h above the Earth's surface. This is the object, and we also need to be familiar with this formula. Small g is equal to capital G times the mass of the Earth divided by radius of Earth square. So G equals gm by r square. Now, how did we get this formula? Well, the weight of the object, let's say the object is on the surface, so there is its weight mg, and there is also gravitational force acting between these two, that is gm times the mass of the Earth divided by the radius of Earth square. Mg is equal to gmm by re square. So m and m get cancelled. So G is equal to G times the mass of the Earth divided by the radius of the Earth square. So now what does the formula for G become? Let me call it G dash. Actually, I'm gonna write it over here only so that I get more space. So G is equal to Gm, well, capital M just means me, that is the mass of the Earth, divided by r square. Now, after going a height h above the Earth's surface, the gravitational acceleration due to gravity becomes gm by r plus h whole square. Because remember, r is the distance between the center of masses of the two objects. So now it's going to become r plus h. So gm can be written as gr square, right? Because look at this formula, g is equal to gm by r square. So gr square equals gm, small g r square divided by r plus h the whole square. Now let us use some mathematics to simplify this expression. Just a moment. Alright, so now notice that this can be written as g divided by r plus h by r the whole square. How did we get this? Well, we are just dividing both the numerator and the denominator by r square. Divide by r square, divide by r square. That's how we got this. And now we're gonna have to use something called binomial approximation that comes from the binomial theorem. So this is nothing but g times 1 plus h by r raised to the negative 2, right? Because if I split this r plus h by r, I get 1 plus h by r. If I take that to the numerator, I get 1 plus h by r raised to the negative 2. Now there's something called binomial approximation. So what is this binomial approximation that we are going to use? Well, the binomial approximation says that, well, this is g dash. Binomial approximation says that 1 plus x raised to the nth power So 1 plus x raised to the nth power is approximately equal to 1 plus nx, where x is much lesser than 1. Apply this binomial approximation over here. So basically the binomial approximation says that 1 plus x raised to the nth power is approximately 1 plus nx for x much lesser than 1. So if we apply that approximation over here, and this h should be much lesser, h should be much lesser than r. So g dash is going to be g into 1 minus 2h by r. How did we get this? Well, 1 plus x raised to the nth power is approximately equal to 1 plus nx. So g into 1, this minus 2 is going to come over here. So plus into minus, so minus 2h by r. So that is the formula that we get for variation of g with altitude. Now let's talk about variation of g with depth. So as we go inside the earth, how does g vary? And one more important thing, this formula g into 1 minus 2h by r is only applicable for h lesser than r by 2, that is half the radius of the earth. If h is greater than r by 2, then you're going to have to use this formula. You just can't do the binomial approximation there. You're going to have to use this formula. This formula is always valid, but this formula has a limitation. As h becomes greater and greater, this approximation is going to get more worse. So it's going to get more and more worse. So for small values of h, it works really good, like 200 kilometers above the earth's surface. It works well. It's a really good approximation. But for h, like if it's 4,000 kilometers, then this approximation is going to fail. Then you're going to have to use the formula that I previously mentioned. Now let's talk about variation of g with depth. Now we are going to assume that Earth has uniform density rho, RHO. It's a symbol used to denote density. So we are going to assume that Earth is a solid sphere with uniform density rho. Now what happens is, when I go below the Earth's surface, so if I go a distance d below the Earth's surface, what's going to happen? So this is the radius. That's actually not the radius. So this is the radius, and this is d. So this is going to be r minus d, right? So this distance is going to be r minus d, and we are assuming that the Earth has uniform density rho. So we know that density equals mass by volume. So we are going to use this formula. So density equals mass by volume. Now as usual, we know that g is equal to gm by r square. Now what is the distance between the object and the center of the Earth? Well, that's just r minus d. So g dash is going to be gm by r minus d whole square. And one more very important thing, This is not the mass of the earth now. Well, since we've gone a distance depth d below the earth's surface, we're going to only have to we should only consider this amount of mass. So we said that earth is a solid sphere with uniform density rho. So we know that density equals mass by volume, so mass equals density into volume. So what's going to happen is that this m is not the mass of the earth now, it's the mass of only this much part of the earth. So how do we figure that out? Well, rho density of the earth, that remains constant everywhere. And what about this? Well, the volume of a sphere is given by 4 by 3 pi r cube. So r here is r minus d, so it's going to become rho 4 by 3 r minus d whole cube times pi, right? So now let us just plug that in. So g is equal to, well, this is g at the surface, that is equal to g, and mass of the whole earth is rho times 4 by 3 pi r cube, not r minus d, because we're talking about the surface, right? Divided by r square. So it's going to become g rho 4 by 3 pi r, g rho 4 by 3 pi r. So now g dash is nothing but g rho 4 by 3 pi into r minus d whole cube divided by r minus d, well, whole square. So what's this going to become? It's just r minus d, g rho 4 by 3 pi r minus d. So now if I find the ratio g dash by g, what do I get? Well, g rho 4 by 3 pi and g rho 4 by 3 pi are gonna get cancelled, so I'm left with r minus d by r, or this can be written as 1 minus d by r. So g dash is equal to g into 1 minus d by r. So this is how g varies with altitude and depth. Now notice that in both the cases the value of g decreases, so the value of g is maximum at the surface. So it decreases with depth and height. Why? Because you're subtracting something from 1. You're subtracting d by r from 1, so it's going to become 0 point something g, and that is always lesser than g, right? And same case, you're during variation of g with altitude, you're subtracting 2h by r, so that was g into 1 minus 2h by r. So you were subtracting 2h by r from 1, so that's always going to be a value less than it's going to be g times 0 point something, which is always going to be less than g. So g dash, variation of g with altitude and depth, both of those, during both of those the value of g decreases. Now let's discuss about the variation of g with rotation, due to the rotation of earth. So let's say this is the axis of rotation. Let's say this is the axis of rotation of the earth. Now let's say an object over here, So this is the equator. Let's say it's making just a second. Let's say it's making an angle phi with the equator. Now what's going to happen is this, due to the rotation of Earth, so let's say this the Earth has an angular velocity omega. So let's say it has an angular velocity omega. So what's going to happen is this object is undergoing circular motion. So this object is undergoing circular motion. And now let me say that the radius of that circle, that is r. I don't want to make it too clumsy. So if you can remember this, the radius of this circle is r. Now, what are the forces acting on this? Well, one is its weight, mg, in this direction towards the center, and there is a centrifugal force. There's a centrifugal force mr omega square. Mr omega square. And if this angle is phi, then this angle is also going to be phi. And if you notice, this is the horizontal component of mr omega square and this is the vertical component. So the vertical component is just going to be mr omega square cos phi, right? If you learnt about taking components along the horizontal and vertical axis, so it's going to be mr omega square cos phi. And this r is not the radius of the Earth, it is, let me call that small r. It's the radius of that circle, this circle that I asked you to remember. So that is small r. Let me change that. So mr omega square cos phi, and this is just, so it's mg, and this is the component of the centrifugal force, that is mr omega square cos phi. Now what is the net force on this object? Well, it is just the net force, let me call that the new, so we can see the variation of g now. So mg dash is going to be mg minus mr omega square cos phi. And notice, this is the radius of the Earth and this is r, this distance. So if you talk about cos phi, that's just going to be small r upon capital R. So small r is r times cosine of phi. So now we can cancel m. So we get g dash is equal to g minus r, and instead of r, small r, I can write capital R cos phi. Remember cos phi, we'll plug that in later. Just now r omega square cos phi times cos phi, cos square phi. So this is the formula for g dash. So this is how g varies due to the rotation of Earth. Now let me make this more clear. What if phi equals 0? That just corresponds to the equator. So at the equator, cos square phi is going to become 1. So we have g minus r omega square. So you're subtracting r omega square from g, so that's obviously lesser than g. So the value of now let's put phi equals 90 degrees. So what is cos 90? 0. So cos square 90 is 0, and r omega square times 0, 0. So g dash equals g. So near the poles, the value of g is maximum, that is g, a small g itself, 9.81 meter per second square. And what about at the equator? It is g minus r omega square. So that is why the value of g near the poles is greater than the value of g near the equator.